Hi, in this video I'm going to talk to you about our 6 degree of freedom trajectory model. All right, so up till now we've been using a vacuum trajectory. Good lightweight way to work out. We can get a lot of reps in with that, right? So now we're moving into 6'd off. All right, this is the heavy lifter. If you really want to understand what's going on with how a projectile moves, this is our complete picture to get everything in there. All right. But it takes a lot more to run these kind of things. If we're doing it on a computer, it's going to be a bit beefier to run all the calculations. Although with modern computer systems, we've got the speed, we've got the capacity. Even though 6'd off models end up needing a lot of kind of numerical methods to get at solutions, we can do that nowadays, and it's a reasonable thing. All right, so it's just some review of some things that are going to come in. So if you think back to your dynamics class about what is angular momentum. All right, so we got angular momentum represented with this letter H, and it just has to do with the moment of inertia multiplied by the angular velocity, right? And if we think about our conservation of linear momentum, all right, a mass times our linear acceleration has to equal the sum of the forces. All right, so we kind of make an analogy from there to the angular side, right? That our angular momentum has to be equal to, instead of a mass, we're talking about this moment of inertia, and we're dealing with the angular acceleration, all right, which is the sum of our moments. All right, so that's how we get at that. Now, a 6 degree of freedom trajectory is what we're going to be talking about today. So this is the full dynamics of the projectile are in play. All right, so not only where is the center of gravity moving, but we also have to think about what is the attitude it's sitting at, how fast is it spinning, where is the nose pointing, all 6 degrees of freedom. All right, so those are 3 linear translations. All right, we've been dealing with those. So how far downrange are we? Where are we located in space? Right, we can go up, down, left, right, and forward, back. Right, but we also have our 3 angular rotations. Okay, so how are we pitching and yawing and rotating our body as that moves around? Okay, some assumptions that come with this model. All right, that our projectile is a rigid body, so we're not going to deal with a projectile kind of flexing as it flies through space. We're going to treat it like just a rigid thing that is there. It can rotate around and move. And has position and rotation information, but it's not bending internally. All right. It has a finite length that doesn't change. All right. So we're not going to adjust or modify the projectile's body itself. Our coordinate system translates. All right. So we're going to put a coordinate system onto the projectile that will move with us. All right. But it doesn't rotate. All right. So even though our projectile is spinning, all right, our y-axis, let's say on the projectile that points up, is going to remain there. All right, so even though the projectile is spinning, we still have an up axis that doesn't rotate around with it. Right, we still have up is up and to the right is to the right. That's not moving with the body, but where in space that origin is moving with our center of gravity. So off of coordinate systems, here is kind of a diagram of how that plays out. All right. So we have unit vectors that move with our body. All right, so I vector is the unit vector that points down the nose along our axis of symmetry. All right, so the tail is negative and the nose points out positive, so that's the positive direction out the nose. All right, so that is our I. Now our other 2 coordinates axes are a unit vector J and a unit vector K. All right, J points generally up to the top of the body, and K is the one that points out sideways towards the right. These are all perpendicular to each other. All right, but again, as our body rotates, we're not going to move that J axis around. It's just the one that was generally up when we started out. All right, we do have this angle there, this alpha t that goes between our axis of symmetry and the vector being right along our trajectory, tangential of that. Now, that's our coordinate system that's moving with the body. All right, we also have a ground-based, earth-based. All right, so we're going to use E's. All right, so E1, 2, and 3 pointing down what would have been our X, Y, and Z axis from our point of fire, right? Where we started from, we can call that earth fixed, all right? But just understand that the E1, the first one, is the one that goes downrange that we were pointing at. E2 is up along our what was our y-axis, and E3 is that one out to the side on the z-axis. All right, so we have both body fixed and earth fixed coordinates that we might be dealing with. All right, some terms that'll come up. I've just got these up on the screen here. These are all variables that we've dealt with in the past, but just wanted to remind you what they all represented. All right, so we have a launch angle, pitch, yaw, and then this total yaw angle that's the combination of the two of them, a latitude, an azimuth when we have to deal with Coriolis, reminder that positive latitudes are in the northern hemisphere. A total angle of attack. We're kind of introducing a fins angle. If you were to have fins or canards, those little things that point stick out on certain, let's say a rocket, typically. But we also have those on sabot rounds, things like that. So what kind of angle are they sitting at? And then a spin rate, P. And we'll talk a little more about that. All right, so some terms to talk about. So the yaw of repose. All right, so we've mentioned that we don't always fly right along the nose line, right? Our nose is generally up, all right, and we get this angle between the tangent and the trajectory, which way we're moving, and the projectile axis once we're stable, all right? So initially we might be coming out and doing a lot of motion that damps down, and we kind of hit this stable point where we're gyroscopically spinning, but things aren't really changing. Now, generally, we're nose up, and that means we've got aerodynamic forces acting against the projectile as it tries to fly, and that is going to create a force on there. Now, if we have a right-hand spin, because we're spinning the projectile, then we end up with a little bit of yaw to the right. So not only are we nose up, but we're also yawed to the right slightly. If we're right-hand spin. If we're left-hand spin, it might be in the other direction, okay? So with the right-hand spinning projectile, we're going to end up with this yaw of repose that's slightly to the right, and our nose is up at the same time. All right. Failure to trail. All right. So failure to trail is when we end up flying base first. All right. So we want to be going generally nose first down. If we're not doing that, we are failing to trail properly. Which means that if we've gotten all the way to apogee and we're still flying backwards, we've flipped over, we've tumbled, that's a failure to trail. Which gives us this thing called a trail angle, which is the maximum angle that our projectile can be at for our yaws, where it'll start to fail to trail. Right? So what is that threshold where we go from staying nose first, and then as that angle increases, at some point the aerodynamic forces will flip us over and we will fly backwards. And that's our trail angle. All right. That is based on the conditions of our firing. So muzzle velocities might change that. What is the QE that we're shooting at, etc. Right? So that trail angle, when we start to fail to trail, will change in different scenarios.